When you think of winter sports, you might think of hockey, skiing, or perhaps figure skating. But what about curling? You know, the sport where two teams take turns pushing stones down the ice towards a bullseye while other team members frantically sweep. Curling originated in Scotland in the 16th century. From humble beginnings on frozen Scottish lochs, the icy game of strategy and dexterity eventually became an official Olympic sport in 1998. Today, it's widely popular in Canada, where even minor tournaments are televised. And its adoration continues to grow in the United States and around the world. Curling is a mesmerizing sport filled with strategy, skill, surprise, a lot of yelling, and science. That's right, science! Getting a curling stone from the start to the house is all physics. Force and friction is what makes it all work. Today we're going to explore the physics at play when you throw rocks down a sheet of ice. Curling is a team sport where players slide stones on a sheet of ice towards a target area called the house. The curler positions their foot to push out of the hack with a lot of force to accelerate with the curling rock. The force from the curler is then transferred to the stone itself. Curling rocks are made of a special granite found in Scotland, and these stones are pretty heavy. They weigh 44 pounds. A handle attached to the top allows the curler to give a stone either a clockwise or counterclockwise rotation when it's thrown. This rotation causes it to curve, or curl, left or right as it moves down the ice. Two sweepers help the stone reach their destination by energetically polishing the ice in front, guiding the rocks to the circle at the center of the house called the button. The team closest to the center after all the rocks are thrown scores points. And if your stones happen to knock your opponent's stones out of the way while you're at it, bonus! The sport of curling depends on three big physics concepts: momentum, inertia, and friction. Momentum is a way to quantify the motion of something that's moving. It's measured as a product of an object's mass and velocity. In order to get an advantage over your opponent in curling, you need to knock their stones away from the button, but make sure that your stone stays within the house closest to the button. This is where momentum comes in handy. But here's another way to think about momentum. If you have two cars of the same weight moving at different speeds, the faster car will have more momentum. But what happens if that car hits something like a traffic cone, which would go further? The object with more momentum will move another object further. And this is important for the curling stones, especially when they collide. When two curling stones hit, there is a transfer of kinetic energy between them. There's also a transfer of momentum, which has to follow Newton's third law of motion. For every action, there is an equal and opposite reaction. You need to get the momentum just right to knock out your opponent and keep your stone in the target. Inertia is the resistance an object has to change its state of motion. Newton's first law of motion states that a body in motion will stay in motion unless it's acted on by an outside force. But what is a force? A force is a push or pull that interacts with another object, which causes it to change how that object is moving. So, if you jump up, you don't go floating into the sky. This is because the force of gravity is pushing you back down to the ground. There are lots of different forces: magnetic forces, elastic forces, like rubber bands, frictional forces, and more. But it's the frictional force that is so important in curling. Friction is the force stopping the motion of other materials sliding against one another. In this case, the stone and the ice. And it always opposes the directional motion of the moving surface. So, in this case, the rock. Imagine dragging something heavy across the sidewalk. Now imagine dragging the same thing across a smooth floor. Which is easier? Surface texture affects how well objects can move across them. The smooth floor has less texture, so it has less frictional force. The sidewalk is bumpy and has lots of texture, so the extra frictional force makes objects harder to drag. So what causes the curling motion? Unlike hockey and figure skating, where the ice surface is smooth, in curling, the ice has a surface similar to an orange peel. If you look closely, the ice has pebble-shaped bumps. Before play, water droplets are dispersed across the ice sheet where they freeze. Then, the pebbles' peaks are shaved off, creating an even running surface with plateaus of different widths. The size and temperature of the water droplets and the intensity of the water spray all affect the playing surface. The bumps give less surface area for the stone to ride on. Less surface contact means less friction. The design of curling stones also play a role in reducing friction. Look at the bottom of the curling stone. It's similar to the bottom of a glass bottle. It's concave, it's not flat. Only a narrow ring at the bottom of the stone, called the running band, actually comes in contact with the ice. This concentrates the weight of the stone onto a smaller area and minimizes the friction, allowing the stone to slide farther. Interestingly, curling is the only sport where you can change the direction of a projectile once it leaves the thrower's hand. Curlers sweep the ice to help the stone travel farther and straighter. Sweeping in front of the stone reduces friction and helps the curlers control the amount of curl the stone undergoes. But why? Take your hands and rub them together. After a while, what do you feel? Friction creates heat, and this heat created by sweeping melts the pebbles. This melting creates a lubrication layer, decreasing the frictional forces and creating a path of least resistance for the stone to glide on. Skilled sweepers can move the stone up to 10 feet further than without sweeping. If they want a stone to travel farther with less curl, they sweep more. If they want more curl or shorter travel, they'll do less sweeping. The physics of curling can become quite complex when you try to account for all the factors that come into play. It's no surprise that it's often referred to as chess on ice. But I think I might need a little practice before my first bonspiel. We saw the role that friction, momentum, and inertia play in curling. But if you want to get first-hand experience to see how friction affects motion, check out our Compact Science Viewer Challenge. We have a fun experiment that you can try at home, creating a mini hovercraft. Get all the instructions on our website and be sure to share your results in the comments. I'm Sarah Jane Gomlak-Green, and you've been watching Compact Science. Until next time, stay curious.
Compact Science is funded by the Joy Family Foundation.
Sheets, ice, woo! Okay. In order to get an advantage, inertia, it's great. Okay. A force is a push or pull that interacts with another object. I said that wrong. Object. It's object. Okay. Yay, curling! I'm sorry.